All right, my apologies. So it seems that I somehow lost my mic during the recording. So I'll try to continue. I believe I was here in selecting the equipment. And I believe I was up to this stage, and I was saying that the software automatically picks equipment that is compliant to the rules as defined in Manual S. So let's head over here. We'll do a Google search for ACA Manual S. Um, in the previous videos, we've talked about Manual J. Currently, we're talking about Manual D. And then only briefly right now, I'm talking about Manual S. Okay, which is, as it says right here, helps to choose the appropriate heating and cooling equipment. Okay. Again, just because you've done the calculations for the heating and cooling loads from Manual J, and just because you've done the calculations for the size of the ducting per Manual D, it does not mean that any machine can be used. Literally to the model number, machines have to be picked. So the software here is capable of automatically selecting um, um, machinery equipment that is compliant to Manual S that will address all the needs for the for this house that we're working on. Okay, so we've got the layout of our ducting system. Okay. What we need to do is we need to specify something called so there's static pressures. Let's go over here. We're going to do external static pressure. Okay. So it refers to the pressure that the fan needs to overcome to move air through the external duct work and fittings. Or you can think of it the other way around. It's the pressure that the system is capable of providing in order to push the air through the system. So let's look at this picture. Okay. Here's our fan. This is the fan that pushes the air. Okay. So return air means the air is getting sucked in through here, through the left side here. It goes through a filter and a coil. The coil is where either the hot or the cold that's produced to the system is transferred to the fan. Okay. And then air goes through the fan, blown out through the supply ducts. Okay. Here's another one. Okay. So think of external static pressure as the capacity, the capability of the equipment to push the air. So that's important because over here we need to define the blower properties. So in the previous recording that got cut out, I had already defined the external static pressure is 0.75. So actually, let me go back. That can only be done here in this tool where it says equipment. Head over to the tab for package air source equipment. And right here in these boxes, you would enter numbers. So let's just do 0.8. Just change it up just for the sake of this video. Okay, I apologize. Like I said, my mic had cut out. All right, now let's head over here to this tool, this static pressure. Here we enter pressure losses for various items. Now, again, let's do a quick Google search. What does it tell us? Okay, so a coil pressure loss, okay, refers to the reduction in static pressure that occurs as air flows through the blower coil. Again, let's look at the images. Okay, so you can see here, this is a pretty good one. Again, so that's going to suck in air from the bottom here and push it up through here. Okay, and eventually at some point it'll come wrap around. And let's go see that it doesn't show us the whole thing. There we go. Okay, so air gets sucked in and then pushed out to the rest of the house. Okay. Each of these things, the individual fittings that I had shown before earlier in the video, these individual items like filters and coils, etc., they all obstruct the airflow. So you can think of it in two different ways. One would be if you have a straw and trying to blow out air through the straw. Okay. If you have an obstruction of some kind, within the straw, like let's say you're bending it or there's something blocking it a little bit, you're going to have to blow harder. You're going to have to push harder. Another way to think of it would be, let's say, a garden hose, okay? You've got water flowing out of your garden hose, and let's say you start to bend it and you form a kink in the hose. It's going to slow down the flow. It might even block it completely, depending on how much you kink it, right? So all of these things here contribute towards blocking or slowing down the flow. We need to take them into account, okay, in what's in the final calculation for friction rate. Now let's head over this section here for a second. You see here total effective length. So according to Manual D, so things that contribute to pressure losses are accounted for in terms of their effective length. So let's say we have a 10-foot length of ducting, okay? Nothing blocking it, it's clear, okay? Now the fact that the air has to move over the metal walls of the duct or whatever the material the duct is made out of, there is some amount of pressure loss. Now over 10 feet, it's minimal. Over 100 feet, it's not minimal. It needs to be taken into account, okay? There's a pressure loss that occurs as the air is flowing. That's because there's friction between the flowing air and the walls of the duct. Again, think about a straw, right? If you're blowing through a short straw, no resistance. Make that straw longer, and at some point you're going to start to feel that resistance, okay? You're going to have to push harder. So same thing with these ducts. Now, a bend in the duct, okay, or some kind of fitting like an elbow like we showed before, or those coils, or the filter, right? These things restrict the flow. We can express how much they restrict the flow either in pressure, okay, using these numbers here, these units here. This means inches of water column. Basically, it means the inches of height of water in a vertical tube, okay, or in PSI. But in Manual D world, we talk about inches of water column, okay. Or we could express the pressure, okay, in terms of the equivalent amount of straight tubing, of straight ducting. So for example, duct bend or duct elbow, okay, all right. So for example, this is a nice gentle 90-degree turn. This is a much tighter turn. So this one would cause us to lose more pressure compared to this one. We can quantify it by saying that, okay, this tight bend would be equivalent to, let's say, I don't know, 25 feet. Actually, Manual D, let me pull that up for a second. All right, so actually, if you go to the Manual D, if you go to ACCA's website, they actually have speed sheets, they call them. These are Excel spreadsheets that you can download. Okay, so they have one for Manual D, they have one for Manual J, Manual S, and Manual N. Okay, so I've already downloaded that, and let's look at this effective length tab. Okay, by the way, I highly recommend downloading it and reading everything that they have. Same thing for Manual J. Let's look at these things here. Okay, so let's find some elbow type of fittings. Here we go. Okay, so this type of fitting, or maybe we'll look at, here we go. Okay, elbows. So a nice smooth elbow might be equivalent to 20 feet of ducting. Okay, a hard bend would be equivalent to 30 feet of ducting. Okay, let's look at some of the other tabs. Okay, so for example here, air comes through here, through this section, and it gets diverted to the left and to the right. Now, you can see here on this side where it says 1B, you can see the air is guided into this duct more smoothly than this one. This is very abrupt. Air doesn't like that. Okay, any flowing fluid does not like anything abrupt. It likes a gentle sort of guiding its way in. So this fitting is equivalent to only 10 feet, whereas this one, because this is much more abrupt, is equivalent to 35 feet of duct, which means we lose more pressure when we have this kind of fitting. In general, we would like to design the system as efficient as possible with minimal pressure losses. Okay, however, we must deal with the realities of the situation that we have, okay, of the particular construction that we have. Also, typically, these more beneficial fittings from the perspective of airflow, they typically tend to be more expensive from a manufacturing perspective. All right, let's head back over here. So in the previous video where I lost my audio, I had already filled these out. Over here it tells us that we are okay. That means that the system is capable of providing enough pressure to get through all of the length of pipes. We have 317 total length of ducting, excuse me, not pipe, ducting. Okay, and it's capable of overcoming these various restrictions in the airflow. All right, so let's head over here to the top where it says supply branches. Now, this is really quite detailed. It deserves some time. Some of the things we need to look for are, so let's look over on the left. We've got the room number. Then we've got the particular supply grill for that room. So room 4 has two grills. Let's look at it. Room 4, where is it? Here we go. We see 2 supply grills. Room 8 also has 2. So does room 6, and so does room 5. Okay. Now we need to know for every supply duct. Okay, that means the particular right here. This duct that is specific to this supply grill. So not the main section here, but just this length right here, just this one that I've selected, okay? And for all of them, okay? We need to know the pressure drop in each, and we need to know the velocity, meaning the speed of the air moving through, and of course we need to know the diameter. So here, this would be equivalent round diameter. It's easier to calculate it from an equivalent round, meaning that the ducting is circular in shape, okay? From this circular shape, we can always convert it to what the real shape would be, okay? Like if it's rectangular, right? So a 7-inch round diameter would be, let's say, equivalent to, I'm just going to throw out numbers here, let's say a 10-inch wide by 4 inches high rectangular shape, okay? What's critical here is that these numbers for velocity, they must be under 900 feet per minute. Otherwise it would create too much noise. And of course we need to know the size of the ducting, okay? And here we have the heating and cooling load for each individual room and for each individual supply grill, okay? If we head over to this tab, we get the similar calculations about velocity, cooling load, heating load, and the diameter for each individual trunk, okay? So the supply line has 2 trunks. So it's got this left side would be 1, and this right side would be 2. Now if you look closely, we can see there's a little triangle here. This means that there's a reduction, a reducer. Here as well, we can see that there's a reduction. A reduction means, let's go over here, it's 12, go to G12. You see that? It means that the duct is changing in size from larger to smaller. Manual J said, they specify in section, I believe it's A8-8, that after the air, okay, so there's air flowing through these ducts. And every time it branches off to some other supply duct, the air starts to slow down a little bit. Once the air has slowed to 50% of its initial speed, then the duct size needs to be reduced in order to maintain an appropriate speed, okay? Now what's nice here is that the software automatically calculates what the sizes should be. I'm going to check this box here for duct notation, and now we can see the size for each duct each individual duct, and also for the trunks. Okay, we can also see the amount of air that's coming out of each supply grill and how much each return needs to be sucking up. Okay, CFM means cubic feet per minute. It's a measure of volume, flow rate of air, right? So a cubic foot. So you take a ruler, X, Y, Z. That's 1 cubic foot. Approximately a shoebox, but bigger, like this, like let's say 2 shoe boxes stacked up, let's say. Um, Approximately per minute. Okay, so each grill is going to have its own flow rate based on what it needs to cool the room, okay, or heat the room. So I was over here. So we see return branch 1 and return branch 2. Let's go look at that. Okay, so we have here, see, these are the different branches for the return. And then over here we have supply trunk 1 and supply trunk 2. And we can see that there's a supply trunk 1A, supply trunk 1B. So you see here, look closely, here's one reduction and here's another. So this is supply trunk 1, okay? And there's 1A and 1B. So after the triangle, this section here would be 1A, and then this last portion here would be 1B. And then this would be supply trunk 2 up till here. From this triangle onward would be supply trunk 2A. And same thing, we have those same limitations on speed. So in any of the supply trunks, the speed cannot be greater than 900. And in the returns, the speed cannot be greater than 700. And you can see that we're pretty close. You may recall from the previous video that when it first generated the layout, it only generated one return grill, and I added a second one. So I'm willing to bet that if I were to delete this one, we would see that this speed would be higher than 700 feet per minute. Let's see. Let's delete this grill. Yep, and sure. Oh, wait a minute. How? How is that possible? That's interesting. I don't know if I trust that necessarily. I have to think about that. I need to inspect it a little further because it's showing that the return branch 1, there's only one of them, does not exceed 700 feet per minute. Oh, because look what they did. They increased the diameter to a very large diameter. Okay. Let's do that again. So here is the return grill. Let's bring it back, and it was somewhere here-ish. There we go. Okay. So let's pay attention to both the speed and the size. So they're quite similar at around right around 630 and 650 with a 14-inch diameter. Okay, so I wonder if I can manually force it. Because it's automatically calculating the duct size. Can I force it to use a particular size for the duct? Maybe. I don't think so. Yeah, I think it's going to automatically yeah. I can't force it because it would be in violation of the rules, okay? But again, so let's real quick. So here we have two, 630, 650, and they're each 14-inch ducts. If I were to delete one of them, head over back to that tab. So now we have not violated the 700 foot per minute requirement, but that's because the software automatically had to bump up the diameter significantly from 14 to 19. Okay, but this means now that the trunk and the register size has to be quite large. Because look at that. Look how much cubic feet per minute of air is coming through it. Okay, so let's bring that back. Let's bring back that second one. All right. All right, so let's go back here. We were looking at this, and okay, right. So over here on this tab, right? So we were looking at the speeds and everything. There's this button here for duct tree. So this shows us um, which room, okay, is served by which trunk. Again, the trunk is the main section, okay, um, and then which return also is provided by the. It's not showing it here, but it does show it visually here. If you head over here, there we go. Okay. All right, so what we've got here is, I guess, 2 videos, 2.5, or 1.5 videos covering Manual D. This is just an introduction. Manual D is full of calculations and methods on how to do something. This was a quick introduction in how to use some of the tools within Wrightsoft in order to produce a Manual D calculation. I highly recommend downloading the speed sheet. It talks about how to use it. It says here a thorough understanding of the Manual D as well as a working, okay, right? A thorough understanding of Manual D is a prerequisite for using this spreadsheet. It really is. Otherwise, you pull it up and it doesn't quite make any sense to you. I mean, it tells you how to use it, but you won't understand anything here. Same for this, right? It's a tool, but you need to know how to use it. So, in order to do that, you'd have to download Manual D. Excuse me, not download. You have to buy Manual D and read it and learn it and familiarize yourself with it. It's not that bad, but it definitely requires reading because there's rules, there's explanations, there's equations and tables and charts and all that good stuff. All right, so that just about sums up this video. If you guys want more videos for this topic, for this Manual D, we can do it. Let me know in the comments, and thank you very much. We'll see you next time.